Welcome to this explainer. Today, we're going to dive into how math shifts from those basic right triangles we all learned about in school to the incredibly powerful circular functions that literally map our entire universe. If you think trigonometry is just about, calculating the height of some ladder leaning against a wall, well, you're in for a really fascinating ride. We are absolutely upgrading our entire mathematical foundation today. Let's get into it. There's this great quote from Milne that perfectly captures our journey today. A mathematician knows how to solve a problem. He cannot solve it. Basically, we're moving way beyond just rote memorization of simple formulas to a true, deep, structural understanding of how trig actually works. It's not just about getting the right answer, right? It's about grasping the underlying geometry that even makes that answer possible in the first place. Historically speaking, the word trigonometry actually comes from Greek, and it just means measuring the sides of a triangle. It started out pretty simply. It was used by ancient sea captains trying to navigate the oceans and by surveyors mapping out new lands. And this whole pursuit was really spearheaded by early mathematical pioneers, folks like Aryabhat, who was laying this foundational groundwork centuries and centuries ago. But today, oh man, its true power extends way, way beyond those early maps and sails. Right now, trigonometry is literally the language of waves and cycles. It helps scientists analyze invisible earthquake waves in seismology. It's absolutely crucial for engineers who are designing electric circuits. It lets us predict the exact types of ocean tides, and it even explains the physical nature of the musical tones we listen to every single day. So the big takeaway here is that trigonometry is really the mathematics of repeating universal patterns. Okay, so to make this complex leap totally understandable, here's our roadmap for today. First, degrees, radians, and arcs. Second, the unit circle paradigm. Third, navigating the four quadrants. And finally, domain, range, and limits. All right, let's jump right into part one, degrees, radians, and arcs. So we're all super familiar with the 360 degrees of a circle, right? But mathematically speaking, 360 is kind of just an arbitrary number. Enter the radian. This is a totally genius unit that connects the geometry of a circle directly to length. Imagine a circle where the radius is exactly 1 unit long. If you take an arc along the edge of that circle that is also exactly 1 unit long, boom! The angle it creates at the center is exactly 1 radian. It perfectly, seamlessly links the distance around the circle directly to the angle itself. Now, because a full circle with a radius of 1 has a circumference of exactly 2 pi, a full 360-degree rotation is equal to 2 pi radians. And from there, we can easily map out a conversion chart. 180 degrees is half a circle, so it's just pi radians. 90 degrees is a quarter circle, so it's pi over 2, and so on. Honestly, it's a remarkably clean system once you get the hang of it. But what's conceptually fascinating here is that the radian measure is tied directly to arc length. This allows us to equate angles with standard real numbers. Think of it like taking a standard, straight real number line and just wrapping it, like a flexible rope, entirely around our unit circle. Every single real number corresponds precisely to a radian measure along that curve. Radian measures and real numbers basically become one and the same thing. Okay, so how does this new unit actually solve real-world problems? Let's look at a practical example directly from our source material. Imagine the minute hand of a watch that is exactly 1.5 centimeters long. We want to know the exact physical distance its tip travels over the course of exactly 40 minutes. By translating the time into a radian fraction, the math becomes incredibly elegant. Let's break it down. Step 1, 40 minutes out of 60 is 2/3 of a full revolution, right? Step 2, since a full revolution is 2 pi radians, 2/3 of that gives us an angle of 4 pi over 3 radians. Finally, the formula for arc length is just the radius multiplied by the angle in radians. So 1.5 centimeters times 4 pi over 3 gives us roughly 6.28 centimeters. It's simple, it's direct, and it's super powerful. Moving right along to part 2, the unit circle paradigm. In early geometry, sine and cosine were strictly ratios of sides in a right-angled triangle. You know the drill, opposite over hypotenuse, adjacent over hypotenuse. But the problem is that only works for acute angles. To expand trigonometry to handle any angle, we take a unit circle and place it on a coordinate plane. If you pick any point on that circle, let's call its coordinates A and B, we fundamentally redefine things. The cosine of the angle becomes the x-coordinate, A, and the sine of the angle becomes the y-coordinate, B. This is a huge shift. Sine and cosine are no longer just triangle ratios. They are actual mapping coordinates tracing a circle.
And because we're operating on a unit circle, the radius is always exactly 1. If you drop a line down from your point to the x-axis, you instantly form a right triangle, where the sides are a and b, and the hypotenuse is 1. Now, thanks to our good old friend the Pythagorean theorem, this guarantees that a squared plus b squared equals 1. Or, putting it in our new language, cosine squared of x plus sine squared of x will always equal precisely 1, literally no matter where you are on the circle.
And from just those two fundamental circle coordinates, sine and cosine, we instantly unlock the rest of the trigonometric functions as simple reciprocal ratios. Cosecant, that's just 1 over sine. Secant is 1 over cosine. Tangent becomes the y-coordinate divided by the x-coordinate, so sine over cosine. And cotangent is just the reverse of that. The whole shebang stems from that single point moving around the unit circle.
All right, let's head into part 3, navigating the 4 quadrants.
By looking at the coordinate plane, we can really easily see how the positive and negative signs work for all these functions. In the first quadrant, both x and y are positive, so sine, cosine, and tangent are all positive. But move over to the second quadrant, and suddenly the x-coordinate goes negative. That means cosine is negative, and because tangent is sine divided by cosine, well, it becomes negative too. In the third quadrant, both coordinates are negative, meaning tangent flips back to positive. And in the fourth, only the x-coordinate, cosine, is positive. It all just perfectly, logically follows the grid.
And honestly, here is where the application to real-world waves really clicks into place. Because we're tracing a closed loop every single time you rotate a full 360 degrees, or 2 pi radians, you end up at the exact same physical point on the circle. That means the output values endlessly and predictably repeat. If you add any integer multiple of 2 pi to your angle, the sine and cosine values remain absolutely identical. This natural periodicity is exactly why these functions are so perfect for modeling repeating cycles in the real world, like sound waves or the changing seasons.
And finally, let's wrap up with part 4, domain, range, and limits.
So the absolutely crucial point here is the massive contrast between our different functions. Because sine and cosine are just the coordinates on a circle with a radius of 1, they are perfectly trapped. Their values can literally never be greater than 1 or less than -1, even though you can input literally any real number as the angle. Tangent, on the other hand, is a ratio. Its output can shoot off to absolute infinity, meaning its range spans all real numbers. But as a trade-off, its input domain has to be restricted. So why is it restricted? Well, those strange tangent restrictions happen exactly when sine or cosine cross the zero axis, which creates these hard mathematical boundaries. Remember, tangent is sine divided by cosine. If cosine is 0, which happens at odd multiples of pi over 2, like 90 or 270 degrees, you are suddenly dividing by 0. And you know what that means. Mathematics totally breaks down. The function becomes completely undefined. Similarly, cosecant and cotangent break down whenever sine hits 0, which happens at whole multiples of pi. Which leaves us with this final thought for today's explainer. We've seen how just wrapping a simple number line around a unit circle entirely redefines our understanding of space, allowing us to map these continuous, endless cycles. So here's the question. If mastering this single mathematical shift can explain the rhythm of devastating earthquakes and the harmony of beautiful music, what other profound, invisible mysteries around us are just waiting to be translated into the right mathematical language? Keep wondering, keep calculating, and I'll catch you in the next explainer.